చెప్పండి చెప్పండి మేడం. ఓకే.
So, good afternoon to the student friends. Today we are going to have second day of the gate coaching classes in electrical circuits. I am Prof.V.Sankar here. Before we start, I want to give the message to be given to you from the university authorities that you can get the Google form through your mobile. And as you might have done yesterday, you can do the questions. And some of you have given some better suggestions, although I could not get completely the list of the messages forwarded to me of yesterday. They said today and yesterday's this one will be sent to me by today evening. But I got some good suggestions from you regarding audio, visual and PowerPoint presentation. Certain suggestions have been made because yesterday was the trial or first class, which we did not have experience in that in making this particular online demonstration or coaching. So we could rectify certain these things. Someone has commented on even mouse. Now I got the mouse to operate. And clarity wise, of course, yesterday same thing. I have got only the PPT with respect to the handwritten material, but we have made that into slides. Each sheet has been made into 2 parts, and this time, not yesterday's. Yesterday we could not do it like that. Based on the suggestions that have been obtained, Honorable Vice Chancellor and the team of members have given the instructions to us to make the PPTs to be cut into 2 parts of one side sheet to 2 sheets in PPT. So this time we have taken some a little bit extra care, and numbering of the slides also is being provided this day. Okay. So yesterday we have discussed about the basic DC circuit analysis, KCL, KVL, that is Kirchhoff's current law, voltage law, and the source transformation, and I tried to solve some of the gate problems. I understand there are certain queries, but it is not very clear. But I understand it's only partially I got this one. Somehow the MS Word document could not be finally given of the Google form format. Anyway, any doubts tomorrow will rectify it if we receive it by today evening concretely. So that in our next presentation, that is tomorrow, we will try to answer the today's and yesterday's remarks. And hardly 1 or 2 questions I could see, but the complete sentence are not there. ఫర్ ఎగ్జాంపుల్ ఎవరో కామెంట్ చేశారు తెలుగులో చెప్తే బాగుంటుంది కదా అని. అది గేట్ కోచింగ్ క్లాసులు తెలుగులో చెప్పడం తప్పు కావచ్చో ఏదో నాకు తెలియదు, కానీ అర్థం కావడం కోసం చెప్పొచ్చు, కానీ కంప్లీట్ గా తెలుగులో చెప్పడం అనేది ఎలక్ట్రికల్ సర్క్యూట్స్ ఇంపాసిబుల్. ఫ్రాంక్లీ స్పీకింగ్, నేను తెలుగు మీడియంలో చదువుకున్నాను ఇంటర్మీడియట్ లో, అయినప్పటికీ ఈ రోజున వీఆర్ నాట్ కన్వర్సెంట్ ఇన్ స్పీకింగ్ ఇన్ తెలుగు ది సబ్జెక్ట్ కంటెంట్. ఓకే, తెలుగులో మామూలుగా మాట్లాడడం వేరు, దీని గురించి మాట్లాడడం వేరు. ఇంకోటి ఎవరో ఒక క్వశ్చన్ పూర్తిగా వేద్దాం అనుకున్నట్టున్నారు, అది గాషియన్ సర్ఫేస్ అనుకున్నారు. ఎలక్ట్రోమాగ్నెటిక్ ఫీల్డ్ థియరీలో నేను చెప్పలేదు, అది పూర్తి క్వశ్చన్ నాకు రాలేదు, ఒక సింగిల్ హాఫ్ లైనే వచ్చింది నాకు మెసేజ్. దాంట్లో చూస్తే గాషియన్ సర్ఫేస్ అనలేదు నేను. ఒక అది పర్టికులర్లీ ఒక ఎగ్జాంపుల్ చెప్తున్నప్పుడు 3 ఈక్వేషన్స్ అవసరం అవుతాయి, 3 లూప్ కరెంట్స్ అవసరం అవుతాయి. మనకి 2 కరెంట్ సోర్సెస్ కి వాల్యూస్ 1 ఆంపియర్ 2 ఆంపియర్ ఇచ్చారు కాబట్టి మనం సైమల్టేనియస్ లీనియర్ ఆల్జీబ్రిక్ ఈక్వేషన్స్ వేసుకుని కన్సిస్టెంట్ సొల్యూషన్ కోసం గాస్ ఎలిమినేషన్ మెథడ్ కానీ గాస్ జోర్డాన్ మెథడ్ కానీ చేయొచ్చు. ఇటరేటివ్ మెథడ్ అవసరం లేదు, బికాజ్ సొల్యూషన్ ఈస్ గ్యారంటీడ్ అండ్ అప్రాక్సిమేట్ సొల్యూషన్ అవసరం లేదన్న ఉద్దేశంలో గాసియన్ గురించి మాట్లాడాను. అది ఎలక్ట్రికల్ సబ్జెక్ట్ కదా అని గౌషియన్ సర్ఫేస్ అనుకున్నారు. నేను ఫీల్డ్ థియరీలోకి వెళ్ళలేదు, దిస్ ఇస్ నాట్ రిలేటెడ్ టు దట్. I hope I have answered that point. But anyway, full question వచ్చిన తర్వాత నాకు రేపు ఇవాళ ఈవినింగ్ కనుక వస్తే నేను టుమారో ఐ విల్ ట్రై టు గివ్ దట్ ఆన్సర్. ఆ క్వశ్చన్ రాసి రీడ్అవుట్ చేసి దెన్ ఐ విల్ గివ్ వన్స్ అగైన్. ఓకే, దిస్ థింగ్. మిగతావి కొంతమంది ఆడియో బాగాలేదని, వీడియో బాగాలేదని అవన్నీ రెక్టిఫై అయినట్టున్నాయి. సో షుడ్ నాట్ బి ఎ ప్రాబ్లం. నౌ ఐ థింక్ మోర్ ఫార్మల్లీ ఐ విల్ స్టార్ట్ నౌ. సో in continuation to the yesterday's topic, I would like to discuss the magnetic circuits. And although explicitly not mentioned in the gate content, it is part of the continuation of the for understanding the subject. So therefore, I have chosen this not more rigorously. And magnetic circuits, then capacitive, briefly I will explain series and parallel connections, then go to the steady state analysis. The main content in today's topic will be steady state analysis also. That is as applied to the AC circuits. Yesterday we have seen as applied to DC circuits. Under steady state condition, the inductance acts as a short circuit, the capacitance acts as an open circuit. But in transient conditions, it is a different issue. Now, under the steady state condition, we mean to say that AC voltages are being applied. So it is equivalent to stating that it is an AC circuit analysis rather. Okay, that is how I would like to discuss at a later stage. So first I will start with magnetic circuits. You know the basic concept of the self-inductance with L is equal to N5I, where N is the number of turns, phi is the flux linking, and I is the current. So we know that electric current has got two effects, heating effect and magnetic effect. So I am not discussing all those things, but it is because I always keep, it is recapitulation. I use the word recapitulation or punastarana taragathulu antam. Kabatti, so I just give the salient points of the that particular topic and then go for numerical examples of the gate solved problems or very interesting problems. All of them may not be given in the gate, but these are required to be understood for the subsequent analysis. That is how I would like to plan this one. So I start with, so we know when two coils are connected in series, with respect to the resistive circuits, we know that R equal to R1 plus R2 is the equivalent resistance. With respect to magnetic circuits, we need to understand that due to the flux linking with the first current flowing through one of the coils, there is a possibility of linking of the flux linking with the another coil also. So there is what is called mutual inductance by principle of mutual induction according to Faraday's law of induction. Okay. So therefore, those laws more formally you may be studying in machines, DC machines as electrical machines, because completely electromagnetic induced EMF principle, dynamically induced EMF principles, all those things you will be studying. So, but we will discuss here with respect to the circuit point of view. So, it is a prerequisite topic for understanding steady state analysis with respect to the AC circuits, right? So, therefore, this could not be directly classified as steady state analysis or otherwise, it is only component analysis. So, when two inductors are connected in series, which we cannot provide unless the AC source is being provided, it doesn't complete with this. But we will not introduce the concept of the reactance here. That will be introduced in the steady state analysis. Because as I said yesterday, inductance acts as a non-linear element sometimes, a linear element sometimes, and other things. The element which obeys Ohm's law is a linear element, I have stated. But in the DC circuits, under steady state analysis or under initial conditions, neither inductance nor capacitance are linear elements, surprisingly. But here, in the steady state analysis, you are going to identify them as the linear elements. So for that, first, the principle of the magnetic circuits is necessary. So when two coils are connected in series, because of the mutual induction, the equivalent inductance is not simply the arithmetic sum of the L, that is L1 plus L2 is not the equivalent inductance. That can be due to the mutual inductance also. That is, the current, due to the current flowing in L1, there is a magnetic flux that can be linked with the inductive coil 2, or due to the current flowing through the inductance in second coil, there is a possibility of getting the mutual induction in the first. So therefore, that is why it is called mutual inductance. So for this, we have to necessarily know that it is not simply the arithmetic sum L1 plus L2 plus something, some mutual inductance. What is that mutual inductance? How it is being connected? What is its relations? This is very important. Although formula is very simple, but understanding the principle is very, very important. So for example, I hope the mouse is now visible to you. I could get the mouse. Yesterday it was not there. Sorry for that. And now you can see two coils are there, L1 and L2 are connected in series, and there is a mutual inductance between the two with sign convention that has implicitly being given, not explicitly. That is, explicit ante konda badru kottinattu, implicit ante dantoni imidi unnattu. Okay, so sign convention ante ippudu dots pettam. For every electrical element we have got starting and ending. So starting of the winding, ending of the winding, L1. Starting of the winding, ending of the winding. Or current entering the inducting coil, current entering the inductive coil. Ikkada koste current leaving the coil, starting, ending. Ikkada starting, ending. So sign convention em cheptundante current entering the coil in both the coils will give same aiding the flux. So therefore, current due to the current flowing in L1, there is a mutual inductance in L2, and due to the current in this one, because it is same direction, because it is series circuit, same current will flow through in both the elements. So the current entering in both coils is taken as positive, right? You can make the connection in such a way, right? Current leaving in both coils is taken as positive. That is, if you put the dot convention here once and another one here instead of these two, then both sides current is leaving the coil, or in other words, the direction of the current is in this direction both, that is in the anti-clockwise direction. It is implied. So because the direction of the current in L2 and L1 will be same in that context, although the current is leaving both the coils, still the mutual inductance between them will be aiding with respect to each other. Okay, it aids, AIDS. It is not a abbreviation, it is only a word. So you have to differentiate between the because people might mistake us if we talk about medical terms, AIDS. No, it's not that. It is aiding. Sometimes in verbal form we take that as AIDS. So it is only a word but not a abbreviation. You should differentiate between the word which has got some meaning and abbreviation. So therefore you should not use capital letters wherever not necessary. Here it is only a word, aiding or aids. Okay, so current entering in both coils M is taken as positive, current leaving both the coils is taken as positive. Current entering, for example, if you have got current entering here and a dot is being put here, for example this, right, in this, the second figure. So current is entering in L1, current is leaving L2. Although this wiring diagram has not been shown, it is possible if I cut it here and then put the end point to the second end point and beginning to the this one, that is this one. So that wiring diagram has not been shown here. It is possible to have the two inductive coils in series opposition. Earlier that is called, this figure is called series aiding, this is called series opposition. So in completing series opposition, current leaving in one coil and current leaving another coil, entering in one coil, leaving another coil is negative. Similarly, current leaving and current entering in the other one. So wiring diagram has not been shown, is negative. So these are the four possibilities in sign convention in the inductances are connected in series, aiding. Now similarly, in the similar context we can use the same thing, but here you can see this is series opposition. So L equivalent equal to L1 plus L2 minus 2M here, and series aiding L is equal to L1 plus L2 plus 2M. So because of that, actually there is a big derivation for this. The M12 is the mutual inductance between first coil current to the second coil induction, and M21 is due to second coil to the first coil, which is proportionality constant is K. K is equal to square root of K1 into K2. If K12 equal to K2, that is coefficient of coupling, is same between these two, which is normally that is expected because both are showing similar properties of the same identical material coils. We don't talk about again the materials here, but from circuit point of view. So finally, with L1, L2 are the self-inductance of the individual coils. M is the mutual inductance between the coils, where M12 equal to M21 is equal to M. Then we have got the coefficient of coupling equation is M is equal to K into square root of L1, L2, or K equal to M by square root of L1 into L2. Ideally, this equation would have been M12 into M21 is equal to K12 into K21 into square root of L1 into L2. So when M is made into L1 into L2, so M12 into M21 is equal to K12 into K21 into L1 into L2. So when you take square root, M is equal to, if M12 equal to M21, it becomes M while taking square root. So similarly, K12 into K21 equal to K is coefficient of coupling is being taken as common between the two coils, then it is equal
అవునవునవును మళ్ళీ రియాక్ట్ ఉంటుంది. పాస్ అయిందంట సార్ అది స్టాప్ అయింది. సార్ అయిపోయింది ఇది కనబడుతుంది. ఓకే ఇప్పుడు చేయించుకోండి ఇప్పుడు చేయించాను సార్ అసలు లేదు. ఇప్పుడు ఓకే ఓకే
Hello, sorry for the interruption. Now I hope I am audible to you all, everyone. Yeah, now I am discussing the point number C with three inductive coils are connected in series. Yeah, so now the dot convention is here. Coils 1 and 2, I have shown it as current entering in both the coils. Now you can see the triangle. Current leaving inductive coil 1 and current entering the third coil. So here both are in opposite direction. Current leaving, current entering in different coils. So that will be minus sign. Then similarly, the rectangle or a square wave, square identification symbol, square symbol is being shown here. For the L2 is current leaving and current entering in the third coil. So these two are minus. That is between 1 and 3, between 2 and 3 is minus sign, between 1 and 2 is positive sign. So the equivalent inductance using the sign convention is sum of the individual inductances L1 plus L2 plus L3 plus 2M12 minus 2M13 minus 2M23 based on the sign convention. Right? I hope it is clear because it is based on the dot convention. So just L1 and L2 have been considered in the earlier case. With sign convention, both entering or both leaving is taken as positive. Opposite, that is entering on one side and leaving on the other side, is taken as a negative in brief. So therefore, the equivalent inductance in series aiding will be L1 plus L2 plus 2M, and in opposition, series opposition will be L1 plus L2 minus 2M. So for sake of continuity, I am just repeating the sentence because there is some interruption. Sorry for the inconvenience that. Now in the 3 coils in series, again the dot convention shows that if the 2 coils are entering with the dot circle that is being shown here is series aiding, and for the between 2 and 3 it is square. Current leaving coil 2, current entering coil 3 is in opposite direction, and between 3 and 1 or 1 and 3 it is a triangle that is being current leaving inductance 1 and current entering the L3. So the equivalent inductance is not the arithmetic sum here, it is L1 plus L2 plus L3 plus 2M12 minus 2M13 minus 2M23. Now similarly, in the parallel connection, this is called parallel aiding and parallel opposition. Okay, parallel aiding I have defined as LAP, and so you can see here both the coils current is entering in the parallel circuit. So there is a derivation for this which I am not doing. So LAP is the equivalent, parallel equivalent inductance when it is aiding, mutual inductance is aiding, is given by L1 L2 minus M square by L1 plus L2 minus 2M. And in you can see in the other one parallel opposition LOP, I have given the notation. So it is current entering inductance and it is current leaving L2 in the inductive coil. So the derivation gives the final value of the derivation is L1 L2 minus M square by L1 plus L2 plus 2M. So I tried to write here, but it is same formula. It's not M equal to K. Sorry for that. M equal to K into square root of L1 L2. While writing it is missed. So sorry for that. Otherwise, it is M equal to K into square root of L1 and L2. Same thing as in the case of the inductance. Now, briefly, I would like to mention about the capacitors in series, capacitors in parallel. It is well known that when 2 capacitors are connected in series, and 2 capacitors are connected in series, C equivalent is C1 C2 by C1 plus C2, and they are connected in parallel, they get directly added up. C equivalent is equal to C1 plus C2. Right, now I will try to work out the problem. This is a brief introduction about the inductance and capacitors. I am not discussing about the formula for the inductance, formula for capacitance and other things from purely circuit point of view, because it is a prerequisite topic for the actual topic of the steady state analysis, which I am going to discuss subsequently. But before that, I would like to solve some of the examples in the gate or other exercise problems which are being given or which are of interesting. I have selected some of the problems. So now I will read out the statement of the problem. Given 2 coupled coils L1 and L2 with their mutual inductance M satisfies M is equal to square root of L1 square plus L2, M is greater than L1 plus L2 by 2, C, M greater than L1 square root of L1 into L2, and M is less than or equal to L1 into L2. So I repeat the question. I hope you are able to see it better as compared to yesterday. So it is a given in GATE 2011 question paper. So given 2 coupled coils L1 and L2 with their mutual inductance M satisfies M is equal to square root of L1 square plus L2, M is greater than L1 plus L2 by 2, C is M greater than square root of L1 into L2, M is less than or equal to L1 into L2. So in general, the coefficient of coupling formula is M by square root of L1 into L2, or M is equal to K into square root of L1 into L2. So that means K, the value of K, it is well known in the general theory of the mutual inductances of the coefficient of coupling. The coupling can be up to 100%. That is, the value lies between 0 and 1. If it is nearer to 0, it is weakly coupled. If it is nearly equal to 1, it is strongly coupled. So therefore, M should satisfy that the value of the K should lie between 0 and 1. So it should be less than or equal to L1 into L2 is the right answer. Because K cannot be, in the C you may be tempted to write because M is greater than square root of L1 into L2 if K is greater than 1. But K value lies between 0 and 1 because the coupling coefficient lies values between 0 and 1, that is no coupling to 100% coupling. So the value lies between 0 to 1. So therefore, if no coupling, it is 0. So therefore, the answer is D. I hope it is easy to follow. So the next question is the mutual inductance between two coupled coils is 10 millihenries. If the turns in one coil is doubled and in the other halved, then the mutual inductance will be 5 millihenries, one answer, 10 millihenries, 14 millihenries, 20 millihenries. And I repeat, the mutual inductance between the two coupled coils is 10 millihenries. If the turns in one coil are doubled and in the other is halved, then the mutual inductance will be 5 millihenries, 10 millihenries, 14 millihenries, and 20 millihenries. Now, there are, it can be easily seen based on the justification. There will not be any change because of the reason that you can see why it is so. You know, L1 is equal to N1 square by S. S is reluctance. N1 is the number of turns. So when it is doubled in this case, the new L1 will be 4 times, whereas L2 will be N2 square by S. The number of turns are halved in this case, so proportional to square of that. So this should be N2 square by S. So 1/4. So 1/4 into 4 getting cancelled when it is the product, so it is equal to the same. So I hope you are able to follow. So in order to answer this particular question, you should know that the value of the when the number of turns are increased or decreased, the inductance is proportional to the square of the number of turns with the same reluctance. It has not been mentioned about the reluctance here. So the reluctance is taken as constant. So therefore, the self-inductance is proportional to the square of the number of turns associated with it. So therefore, when once is doubled, its value is 4 times. And it is second one, it is halved, its value is 1/4. The product of this L1 and L2 in the new one is going to be same. Therefore, the mutual inductance between two coupled coils is also going to be the same, is equal to 10 into millihenries, because M is equal to K into square root of L1 L2. K is assumed to be 1 indirectly in this case. So this is the answer. Any clarity is required, you can write down the Google form, then we will answer that. So these are some of the typical problems that I have taken from self-inductance and mutual inductance problems. Some more you will get in subsequent chapters also, where I am preparing in resonance also. Very, very important topic. Subsequently, we will discuss in the next class. Now, problems in capacitor, because this is a prerequisite one for steady state analysis at about start for AC circuit analysis. So, a brief, some of the questions that are being I have selected may not be given in GATE because but it is for practice session, and for continuation of the subsequent topic I have selected these 2 or 3 questions. I will explain, then I will go to the steady state analysis. So because there was some interruption today, maybe I may extend if necessary by 10 minutes because there was interruption for about 10 minutes. So total capacitance, the question is, the total capacitance of 2 capacitors is 25 farads when connected in parallel and 4 farads when connected in series. The individual capacitance of 2 capacitors are, so it is given 4 multiple choice answers. The first A is 1 farad and 24 farads, second one is 3 farads and 21 farads, and 5 farads and 20 farads, 10 farads and 15 farads. So I repeat the statement of the problem, because generally you are expected to do this within 30 seconds or maximum of 1 minute. So I repeat the statement of the problem. In the meantime, you can try to think about the solution, which is already given, but you can see these are generally given for 1 mark questions only. Okay. But anyway, these although answers are being given in some of the question bank, these things, but no solution is being given. So if anything wrong, There may not be wrong because we have solved it correctly, and the answer is tallying with the answer that is being given in the question bank. About 15,000 bits are there. J.B. Gupta or even in some other book called Harish Roy and Ashok Ross. So from there we have done and solved the problems by myself, and because it is logic is correct, I assume that these things are right. If anything is there wrong, you can debatable. You can send in the Google form about that. We will discuss, and whenever in the appropriate time, I will discuss those things. So we will discuss the clarity. Do not get carried away just because the teacher has given you these solutions. Okay. Anyway, anybody can go wrong, but as far as possible, we try to do it correctly. Okay. So I repeat the statement of the problem. Total capacitance of two capacitors is 25 farads when connected in parallel and 4 farads when connected in series. The individual capacitance of two capacitors are, the choices are given. Now, the solution methodology is as follows. I hope you might have got the idea by now. So I am giving the solution now. This is one type of solution I got. If any other thing is there, if it is correctly made, we welcome that. Do not get carried away with the solution which we are giving. If it is beyond that, you have got another way of getting it. It is always a welcoming feature. So let C1 and C2 be the capacitors. When in parallel, we know that it is sum of the capacitances. So C1 plus C2 is equal to 25. So when in series, it is C1 C2 by C1 plus C2. So C1 C2 by C1 plus C2 is equal to 4. That is C1 C2 equal to 4 into C1 plus C2 is 4 into 25 is 100. Okay, this is 100, 100. So it's not 10, sorry, it is 100. Now, to solve, because now we have to get two equations. One equation C1 plus C2 is 25. And we need to get another equation so that we can get C1, C2. We know from algebra that C1 A minus B whole square is equal to A plus B whole square minus 4AB. So AB are C1 and C2 here. So C1 minus C2 whole square is C1 plus C2 whole square minus 4 into C1 C2. So C1 plus C2 is 25. 25 square minus 4 into 100 is 225. So C1 minus C2 is the square root of that is equal to 225 and C1 C2 is equal to 15. So C1 plus C2 is 25, C1 minus C2 is 15. So adding you will get 2C1 is 20, that is 10 farads. And subtracting from subtracting you will get 2C2 is equal to 2C2 is equal to 2C2 is equal to 10, so it is 5. So 5 farads and 20 farads, yeah. There is some 25 and 4, so maybe I might have written here wrongly, but this is right on. You can see answer is given as C, so it is tallying with 5 farads and 20 is given. It is here I have written wrongly. Yeah, sorry. 2C1 is 40, 25 plus 15. That is where, while writing I might have done a small mistake here. So 25 plus 15 is 40, is 2C1 is 40, so C1 is 20. So when you subtracted 25 minus 15 is 10, so it is 5F. So sorry for the inconvenience. So C is the right answer, 5F and 20F. Here it is 2C1 is 40. There is error here. Now I cannot correct it because it is an image that is being dumped into the PPT point. Sorry for the error. So it is C is the right answer. So I will take another simple example. There are 6 capacitors of different capacitances C1 to C6 are connected in series. Given C1 is greater than C2, greater than C3, greater than C4, greater than C5 and greater than C6. What is the capacitance almost equal to? Either C1 or C3, C4 or C6. 4 multiple choice questions are being given. It is not of the gate standard, maybe or may not be of gate standard, but it is given in some of the IES examinations or other competitive examinations, engineering services or UPSC examinations. These question papers questions are being given there. Only the object type questions or answers are being given, but you have to give the solution to that. It may be right or wrong. It is debatable. Okay, right. Anyway, as far as possible, I have done it to the best of my knowledge correctly. Any ambiguity is there, we will try to rectify that. So 6 capacitors of, I repeat the statement of the problem. 6 capacitors of different capacitance C1 to C6 are connected in series. C1 is greater than C2, greater than C3, greater than C4, greater than C5, greater than C6. Right? What is the capacitance almost equal to? So the answers that are being given are C1, C3, C4, C6. Okay. 1 by C equivalent is equal to, we know the equivalent capacitance equal to 1 by C1 plus 1 by C2 plus 1 by C3 plus C1 by C4 plus 1 by C5 plus 1 by C6. In general, even in resistors when they are connected in parallel, the total equivalent resistance will be less than or equal to the least resistance of the corresponding one. That is why the current takes the least resistance for people is to say. So in capacitance also, when they are connected in series, it will be less than or equal to the least of this one because of the same principle. So in general, in such situation, it should satisfy that it should be less than or equal to C6. So it is almost equal to means it is less than or equal to symbol we can use. So as it will be less than or equal to or at least the value of the capacitance, since C6 is very less and hence is the answer. So it is simple logic. Needs one more question. That is given in one of the competitive examinations. So I will go to the next question. Now capacitance of each capacitor is 3 microfarads in the figure shown. The effective capacitance between points A and B is, A is here, B is here. 2 microfarad, one solution, 3, 4 and 5. Okay. The circuit is redrawn here. So with A, B, I have identified some more terminals. There is this junction C and D. Okay, the capacitance C is there, but this junction C. So it appears that now the junctions A, then the junction C and D are in delta connection, and then we need to solve this and other things. But luckily, as I observed, if you observe closely, you can see that between C and D, these two capacitors are in parallel. Otherwise, you may be tempted to go to the delta to star conversion, do it, simple equivalent circuits, we have to do it and other things. So I found that this type of solution can be obtained because by observing that there is no element between D to B, although there is a junction that is being shown, it is shown only as a short circuit. So that there is no element that is being shown here. So that gives us some idea that these two are directly connected at this point. So C and C are in parallel. So the equivalent capacitance is 2C. Now between A and D, you can see this 2C and C are in series. So the equivalent capacitance is 2C into C by 2C plus C. It is 2/3 of C. And this 2/3 of C is in series in parallel with the capacitance C in this. So 2/3 of C plus C is equal to 5 by 3 into C, where C is given as 3 microfarads. It is 5 microfarads is the answer. So it is tallying with one of these things. If anything wrong, we will justify it subsequently. It's all tricky problems because the solutions are not being standardized. One may be tempted to choose the one side of solution which we have gone is the final answer. Okay, so always it is arguable or defendable. We need to defend the solution that have been given. So I repeat the solution here. So for this problem, this is particularly being drawn. So it appears that A, C, D are in delta connection, but this also across the point B, D and B are being same. These two appear to be in parallel. That's how I could find this solution. There is no element here. If there is an element between this, then there would be another junction. Then we need to solve in a different way. Luckily, there is no element in this. So therefore, these two are considered to be in parallel. So the parallel equivalent is 2C because some of the equivalent capacitances. Then between AC and CD, now since 2C and C are in series, so therefore the equivalent capacitance 2C into C by 2C plus C is 2/3 of C. Now this C equivalent is in parallel with the capacitor C here. Then C equivalent now will be 2/3 of C plus C is 5 by 3C, and multiplied by C value is given as 3 microfarads. So it is 5/3 of 3 is 5 microfarads. So therefore the answer is D is the solution. So far I have just discussed with respect to KCL, KVL, source transformation and basic properties of the inductance and capacitance. Now this steady state analysis, this is I have classified this as third unit. Okay. So Today's topic will be based on the steady state analysis, that is AC circuit or AC circuit analysis under steady state conditions. That is, we are going to discuss the basic terminology, difference between scalar, phasor and vector. So if you will always get confused between vector and phasor, I will just mention that. Already you might have studied in electrical circuits in fundamental second unit of the first semester course whenever it is being offered. And the basic definitions of these things, and current through the resistive circuit, phasor diagrams of voltage and current, inductive circuit, simple capacitive, RL series, RC series, RLC series circuits, parallel circuits. Up to this point, I would like to discuss in today's discussion. The extension of this one is resonance, that I will discuss tomorrow. Okay, so, and with some solved problems. So I will give only the gist of the corresponding points here. So the steady state analysis is with respect to AC fundamentals, basics of AC circuits. So the definitions, the instantaneous value, peak value, phase of the corresponding alternate quantity, I have not just mentioned that because they are too elementary, and form factor, because this is very important, one of the components to be found out. So this RMS value, the ratio of the RMS to the average value, or effective or RMS value divided by average value. You know, RMS value is definition, and average value I have just given. It is already known to you, and we will just brief it. It is the mean value of an alternating quantity, or the current is expressed by that steady current which transfers across any circuit. The same charge is transferred by that alternating current during the same time. So that is given as the average value. And RMS value is the RMS value or effective value of an alternating current on voltage is given by that steady current on voltage, which when flows are applied to a given resistance for a given time produces the same amount of energy as when alternating voltage or current is flowing are applied to the same resistance for the same time. These definitions are very well known to you. I don't have to explain these things, but sometimes you need to apply them for the different applications which I will mention. Okay. Now I will show some of the properties here. The average value of a pure sine wave, the average value of a pure sine wave is 0 for full cycle. That is expected because the sinusoidal alternating current quantity is assumed to be pure sinusoidal. Okay. If it is not pure, that is why you are struggling with in machines harmonic components, reduction of harmonic components is still a wide open subject problem which power electronics people specialization always deal with that reduction of harmonic components called THD and other things. So anyway, all these things will come in that particular one, and this is that is why I mentioned pure sine wave. That is only consisting of fundamental sine wave. Rest of the harmonics are 0. If it is first year level, this point would not have been able to understand. So the fundamental definition, based on the fundamental definition, the approach of application and understanding is different for different levels. That is a viewpoint which I would like to state here. So the average value of pure sine wave is 0 for full cycle. Sorry, fully cycle is not correct, it's full cycle. Small error. Average value of half-wave rectified sine wave is well known. It is only just not for mucking up, but it can be easily proved by taking for the average value definition, integrating that and other things is 0.318 times its peak value. Sometimes in object type questions or dash type questions, it is possible to be given, so I have collected that information. Anyway, nowadays the questions are becoming, because now it is 30 years old, these may not be directly, same repetition will not be there, but it's not that always we have to think in terms of answering the questions. You need to understand the concepts and fundamental points to be remembered for further these things. So by then, average value of sine wave taken for half cycle is 0.636 times its peak value. Average value of a square wave for half cycle is unity. This is very important solution. For rectangular or square wave, its value of the RMS value is unity. And average value, and there is a typical problem based on that particular one, which I will give you in the solution strategy of the object type questions, which is given in one of the GATE examinations. And the average value of a full wave rectified sine wave is 0.63 times its peak value. Average value of a triangular wave is 0.5 times its peak value. So these are the salient points in based on the some configurations. They are already being available as the salient features that are being given. So there are some more points. So RMS value of a sine wave is of course is well known, is Im by root 2, means Im is peak value divided by root 2. and the RMS value of half wave rectified sine wave is Im by 2, half of the peak value. RMS value of full wave rectified sine wave is Im by root 2. RMS value of square wave is unity. RMS value of triangular wave is 0.5 times the peak value. Now, I will discuss with single phase circuit, series circuits. That is now under steady state condition. Now, the frequency of the source is 50 Hz, that is well known, and it is I is the instantaneous value of the current, R is the resistance, and V is equal to Vm sin theta or sin omega t. It is well known, the standard way of writing it. But with respect to writing the phasors, it can be written with respect to the peak value or RMS values. Okay, once it is defined for peak values, later we convert them into the RMS values. Always RMS values are being taken into the corresponding phasor diagram. Now I would like to differentiate between scalar, a vector, and a phasor. Scalar is of course a multiple and vector like, which is dimensionless or no directionless quantity. It is a magnitude, it is a scalar, it is a multiplier like. A vector is having a direction with some magnitude. But what is a phasor? Phasor looks like a vector, but its value resembles in one cycle of the sine wave in positive half cycle and negative half cycles. Imagine between a pair of poles the armature is rotating. Take a DC machine or any machine. So when it is conductor is rotating in anti-clockwise direction in the vicinity of the magnetic poles, in the first quadrant, okay, imagine it is in anti-clockwise direction in the first quadrant. When the magnetic flux is in parallel with the corresponding conductor, then no cutting of the flux, so EMF induced is 0. So this particular position, say OB, although it is shown as I, is the current, for example, the horizontal position is the initial phasor position. Although it is a vector, but it's represented as phasor. That means the vertical projection of this onto the vertical axis, that is the projection of OI onto the imagined vertical axis, is 0. And similarly, if it is somewhere in between, then you will get subsequently at an angle of I cos phi, and when it rotates by 90 degrees in counterclockwise direction, becomes peak value and other things. So just as one sine wave is being obtained, written, correspondingly the phasor rotates through the one cycle of revolution for the entire these things in 4 quadrants, so 360 degrees. Therefore, a phasor is being represented as a vector whose position value is being considered as one rotation is equivalent to one cycle of the EMF that is being generated or one cycle of the current that is being shown, because it is alternating current quantity. Now, one more interesting property which is absolutely necessary to remember is that phasors of same frequency only can be drawn on the same plane. I repeat, the phasors of the same frequency components of the voltage and currents can be drawn on the same plane. That means you have got a frequency of F, and there is another component of 2F frequency. The current component can be according to Fourier series expansion A naught plus sigma A n cos n omega t plus B n sin n omega t. The second and third frequency components are referred as harmonic components. So that Fourier series is referred to this. But in first year level, if it is subject to be taught, those things will not be mentioned. But in third year and final year level, you understand the difference of these things. So that is why we assume that the component frequencies are in the same frequencies. Then only we can go for same plane diagram. So that is important property. Anyway, these are simple things. The voltage and OA is taken as V, OB is I. For the resistance, both are in phase components. The phase difference is 0. In phase means the phase difference are 0. That means the peak values occur simultaneously. Okay. And power factor is unity. So Anyway, we have got the slide numbering also, although it is not shown here. You can refer to the slide number if at all you have got any doubt subsequently. Now, I go to the purely inductive circuit. Right? So, it is well known that current lags the applied voltage by 90 degrees. Right? So, with saying the voltage is taken as the reference phasor, current lags behind. Lagging quantities are shown as clockwise, leading quantities are shown in anti-clockwise. Okay? Leading is over the in the first quadrant and lagging quantities in fourth quadrant. Right. So, the average power is 0, that is power factor is also 0 if it is pure inductive. But you will see subsequently that this is inductance implies it is pure inductive coil, no inherent resistance of the inductance. But in practice, there will be some internal resistance of the inductive coil. Otherwise, the source gives you inductance acting as the corresponding under steady state condition. Okay, no problem. But if it is pure inductive coil with the resistance is being 0, then the average power will be 0. The current lags the applied voltage. It gives you VAR component, that is volt amp as reactive. That anyway you are going to just briefly mention it. But anyway, you know that concepts already. So anyway, current lags the applied voltage by 90 degrees. So it is a power loss component, powerless component, right? That means no real power loss will be there in this. It is only reactive power loss. So those things you are aware of that. So average power is 0 and power factor is 0. XL is inductive reactance. Now this is where I need to mention the difference between the steady state components and the property of the inductance. In the DC circuit analysis, I have mentioned that in initial conditions and final conditions it is acting as open circuit or short circuit. Here it is offering the, that is L is in henries, omega is 2 pi of f is doing frequency, omega is angular frequency in radians per second, which is well known to you, is omega L is equal to XL, is known as inductive reactance. So inductive reactance, it is written as reactive, sorry. So it is reactive nature. So it is inductive reactance is REACTANCE, not reactive. Okay, inductive reactance is taken as in ohms. That is the ohmic value of the inductance is known as the inductive reactance. So when it is set as ohmic value, whose value is in ohms, then it automatically follows Ohm's law. So V is equal to I into XL. So VY is not equal to resistance here, is VI equal to XL. So in polar form, in Cartesian form, we can write these things. In polar form, magnitude of I at an angle of minus 90 degrees, we write those things. You are aware of that. So I briefly mentioned those things here. So similarly, in the capacitive circuit, current leads the applied voltage by 90 degrees. So this is the typical one. Even though current is given instantaneously, the current leads the applied voltage by 90 degrees. Okay, under steady state conditions. You know, imagine 50 cycles per second, right? And average power again for taken for a full cycle is 0. And the capacitive reactance is 1 over omega c, 1 over 2 pi f c, and power factor is 0. F is the frequency, and this gives in ohmic value. So I into X equal to V or X equal to V by I is not the resistance, it is a ohmic value which is called capacitive reactance, right? So it is well known now. In a resistive circuit, the voltage and current are in phase. In the inductive circuit, pure inductive circuit rather, current lags the applied voltage by 90 degrees. In the capacitive circuit, current leads the applied voltage by 90 degrees. Now these are very, very important concepts which you might be familiar, but still we need to explain them so that everything depends on RLC circuit parameters and the corresponding solution strategies and other things. So in this, it is a series RL circuit. So we will discuss RL series, RC series, RLC series circuit, and some of the parallel connected circuits also. Then work out some of the problems which are given in gate or other equivalent these things. Okay, yeah. So here R is this one, L is this one. the voltage, this is VR, voltage across the resistance, this is VL, voltage across the inductance. Now again you have to remember that V is equal to VR plus VL, not. No, it's not directly, because it is not the arithmetic sum, it is a phasor sum. Although we represent in terms of that, VR plus VL is sum of that, but it is a VR plus JVL. And J is a phasor which I will give basic relation subsequently. It is given later, but you know J is a phasor which is 180 angle 90 degrees in counterclockwise direction in phasor form, and J square is 180 angle 180 are equal to -1, same as J equal to square root of -1, which is a complex quantity. So we correlate that side of square root of -1 into the complex quantity as a phasor with J operator. Similarly, in three-phase circuit, you will get A is the operator, that is well known. So directly I am going this because it is only just recapitulation, revising the course content for solving the problems. So I do not want to take much of the time in this. These are very fundamental, so I hope you are aware of these things, because you might have already studied also for your gate preparations. But anyway, it is just again memorizing these things for sake of continuity only, right? So the impedance, this is called voltage triangle. So V is equal to VR plus JVL, because you can see I is taken as the reference because the current is in series with both the components, and you got the simple current is having two components now. That is real part of the component and reactive part of the component. That also can be understood in this particular one. And V is equal to VR plus total applied voltage. V is equal to VR plus JBL. F is the frequency. And here you can see the voltage triangle. I is taken as reference phasor. VR is I into R, not to the magnitude that have been written here, but it is representation. And VL is exactly 90 degrees, slightly, now I observed that there is slight deviation, but it is taken as perpendicular line. So leading by 90 degrees with respect to the current. And the resultant current is VR plus JVL is V at an angle of phi. So it is lagging power factor angle, because current lags the applied voltage, right? So the real power consumed is VI cos phi is in watts, and QA is called equal to VI sin phi, product of the RMS values. I have not given phasor notation here by putting the top of it arrows, but anyway, we could have put on the top side of it arrows. Some textbooks print that as the bold face letters and black bold letters and other things. Simply by standard convention, in the written text, we take capital V and capital I are the RMS values, and they are represented as phasors in one stroke. Instead of going for too much of mathematical notation here with that simple sentence, because we know the difference between that, so we are going ahead with that. They are not scalar quantities, they are phasors. So everything should have been written V bar, I bar and other thing, so which we are trying to eliminate for simple sense. Otherwise, they are not simply the magnitudes in the normal scalar quantities. That anyway, I am giving clarification, so it doesn't matter. So as long as there is a clarity and we define consistently of the corresponding quantities, should not matter. So because there is no need for any confusion in this, because some standard textbooks follow different notations here, but for convenience we have chosen V and I only as the phasors here, not the scalar quantities, right? So VI cos phi, phi is the phase angle difference between the voltage and the current. Similarly, VI sin phi is in watts, volt amperes, reactive itself is the unit for that. And S is the complex power, is also called as apparent power in volt amperes. So this is the power triangle, this is the impedance triangle, and this is the complex power, the unit is volt amperes. So volt amperes, S into cos phi is real power, S into sin phi is reactive power in watts. So power factor is cos phi, phi is equal to tan inverse of XL by R, and XL is equal to omega L. So omega L by R, tan inverse of XL by R, omega L by R. So P equal to S into cos phi, Q is equal to S into sin phi mentioned, and this is the current triangle. Now we can see current triangle means with reference phasor that is being chosen as some quantity. If you want to get the components of the current, I is actually the real power component of the, that is the component of the current which is in phase with the applied voltage which gives the real power loss, is IR, the real power current. That is real power component of the complex current, right? That is typical. So similarly, inductive current. What is inductive current? The quadrature component of the current which is in quadrature with or in phase with the inductive voltage, in phase with this voltage, is the quadrature component of the current. So it is the components, real power component, the reactive power component of the current. which gives you I. But this I is the same, but which is taken as the reference phasor here. But these are the components of the current. So these things you might be familiar, but it is only just, as I said, it is recapitulation. I hope you are able to follow me. And one more important factor to be remembered in this is Q factor. As per the sections, I have split the full text of the sheet into two parts. That is why you are getting this as a simple one slide or one sentence only. So, because yesterday there was comments that it is not readable, so we made the text into parts, and we have made as one of the sheet as 2 slides in PPT presentation. I'm sorry I could not make PPT because you are going to follow the circuit subsequently. Still, we have to get familiar with drawing the circuits in PPT. Maybe whenever time permits, if I give the opportunity next time, and then next phase of these things, whenever we may have to repeat, or then we may come back with that solution. Now we have to learn that we need to understand that software. People say some softwares are available to draw that. We'll try to do that subsequently. Sorry for the inconvenience for this phase 1. For the next 10 days also, I may not be able to do that. Sorry for the inconvenience. So please bear with me in this context. So Q factor is 2 pi into maximum energy stored divided by energy dissipated per cycle. That definitions are there. Everything is known to you. So it is equal to omega L by R. The quality factor, Q factor is essentially also refers to at a later stage selectivity, bandwidth, and other things in resonant circuits. But anyway, for a series oral circuit, Q factor also can be obtained as a salient point, which I just mentioned here. So next one is RC series circuit. So in the RC series circuit, similarly the notation here is V is the RMS value is applied voltage, F is the frequency, VR is the voltage across the resistance, VC is the voltage across the capacitance, I is the total current, which is common. And now I have given all the 4 triangles. You can see, right? 3 triangles here. I is the current reference phasor. VR will be in applied voltage, not to the scale, because I is only a reference phasor that is being shown here. So VR will be in phase with the I, so it is VR. And VC will be with respect to the current. Earlier I said current will be leading the applied voltage. Now with current is chosen as reference, the quadrature component of the voltage across the capacitance will be lagging by 90 degrees. So the net resultant voltage V equal to I into Z will be lagging with respect to the current, that is phi C. Actually it is leading current with respect to the voltage. But with respect to the voltage, of course current is leading, it can be seen clearly. But here in the RC series circuit, the convention that is being followed is current is common, but voltage gets divided. So V equal to VR plus JVL in the earlier case, because it is inductive. Here this capacitor circuit, V equal to VR minus JVC. So because it is a quadrature lagging component, so this is minus JVC, minus JVC equal to minus JVC. Okay. Voltage across the capacitor is expressed in phasor form as minus JVC. So Z is equal to R minus JXC is the impedance, and XC is the capacitive reactance, which is inductive reactance is positive, capacitive reactance is negative. These points are very fundamental. One has to remember these things. In the parallel circuits, we will see the other properties of this thing. Z is equal to R minus JXC in the series circuit, and phi C is equal to tan inverse of minus XC by R. So tan inverse of minus 1 by omega R into C. And power factor is equal to R by Z. Current leads the phi C, so it is leading power factor circuit. So P, real power is equal to VI into cos phi C, QC is equal to VI into sin phi C. So this is the impedance triangle, this is the power triangle, and S is equal to P minus JQC. S is equal to complex power is square root of P square plus QC square in magnitude. And Q factor is again equal to, instead of XL by R now, in the RC series circuit it is XC by R. And similarly, in RLC series circuit, because these things are all familiar to you, just as I told you, I'm just putting all at once for the sake of, because the other things are to follow now. I mentioned not to the scale, but it is reference phasor, horizontal, and VR will be in phase with the applied voltage, and VL is the voltage across the inductance, which is leading by 90 degrees with respect to the current that is being chosen as the reference phasor. VC will be quadrature lagging with respect to this one that is being shown here as this. Yeah, this is VC, quadrature component from the VR, and this quadrature leading inductive component. The next one is AD point. Point D is VL minus VC, whichever is dominating. So here the question arises in RLC series circuit. Out of V is equal to VR plus JVL minus JVC. VR square plus VC, VL minus VC square is the magnitude, and Z is equal to R plus JXL minus XC. So this is where we need to understand the circuit behavior. If XL minus XC is greater than 0, the circuit will be called as not inductive circuit, predominantly inductive circuit. It is dominant, that is predominant. So that means it is dominant over the capacitive reactance. So XL minus XC is greater than 0, the net effective reactance. So net reactance is greater than 0 implies it is the net reactance is greater than 0 implies it is inductive component. So R plus JXL. So the net reactance is R plus JX. If XL is greater than XC, that means it is predominantly inductive circuit. It is possible that XC is greater than XL, then the circuit is behaving as the leading power factor circuit. XC will be greater than XL. Here it is shown as only inductively dominant circuit, for example. Okay, but nevertheless, if XC is greater than XL, that is capacitive reactance is more than the inductive reactance, the circuit behaves as a leading power factor circuit. Then in that case, it will be R plus J XC minus XL. That is, so the power factors of the circuit will be leading power factor. And there may case arise, their third option is most powerful option. Also, all three are very useful, and XL minus XC equal to 0. It is possible that net reactance is 0, and the condition of the resonance arises. The resonance itself is a separate topic which I am going to explain in tomorrow's lecture, series resonance, parallel resonance and other things. So, but it is only up to series circuit point of view we will mention. So, the understanding of this now is in RL series circuit, current RL series, in series circuits, RL, RC and RLC circuits are generally taken, and you can have a number of components in series also. But if you make the corresponding impedances Z1 plus Z2, Z3, the circuit may be predominantly inductive, predominantly capacitive, so R plus JXL or R minus JXC ultimately. Except the case where Z becomes R, that is resonance, that we will discuss separately. So therefore, there are only three components in electrical circuits, R, L and C. Resistive, inductive and capacitive. No other this thing. Right? Always we deal with these things or equivalent to this, we always deal with the basic circuit parameters or R, L, C. So purely resistive, predominantly inductive, predominantly capacitive circuits. So in RL series circuit, current lags the applied voltage, power factor is lagging power factor, and we have defined the real and reactive powers and complex power and Q factor also. And similarly, RC series circuit, we have got current leads the applied voltage, and the power factor of the circuit is R by Z, and current leads the applied voltage by phi C. Real power, reactive power, and the complex power and Q factor also have been mentioned. And in RLC series circuit, it is quite interesting that R plus JX minus XC is the total impedance of the circuit. Okay, so these things are familiar to you, but now I want to just mention once again that if XL is greater than XC, the net reactance is positive, implies it is predominantly inductive. If XC is greater than XL, then it is predominantly capacitive. If XL equal to XC, it is no reactance is there, but it does not mean that we will define more formula at a later stage. In spite of the presence of the RLC elements, the circuit behaves as a purely resistive. That is a specific nature of the RLC series circuits. So these points are just written here. Impedance will be predominantly inductive. So already I have mentioned. Anyway, the impedance will be predominantly inductive if XL minus XC is greater than 0. X is called net reactance, is XL minus XC. The impedance will be predominantly capacitive. If XC is minus XL is greater than 0, that is X is less than 0. The impedance will be purely resistive type if net reactance is 0. Power factor is R by modulus of Z. You know the difference between the magnitude. Magnitude of that is real square root of the real part square and imaginary part square. That is a simple right. Now just briefly I have written here to make you understand that we have to use the phasor notation. J is not a simple quantity here. It is equivalent to, in mathematical sense, I is equal to square root of minus, so no doubt about that. And at a later stage, we will talk about residues in mathematics also, is same quantities. But in alternating current circuits, we use the notation J is a phasor, which when it is applied on a particular quantity of the vector, it is implied that the vector with a magnitude of 1 rotates in counterclockwise direction by 90 degrees, in anticlockwise direction by 90 degrees. So similarly, j square means 1 at an angle 180 is equal to minus 1. So therefore, j equal to square root of minus 1 is same complex quantity in mathematics that is being given I equal to square root of minus 1. But I we want to use for small I instantaneous value, capital I for RMS value, Im for peak value of the currents. So we use j notation here instead of I as used by the mathematics people. Right? J cube is equal to minus j is 1 at an angle 270. So divided by 270 degrees, and j power 4 is 1. That means it completes one cycle. J power is same as j square into j square is 1. So it is the same as 1 at angle 0. Again, j power 5 is j. Like that, second cycle starts. So like that, we can obtain the j notation. So one complete revolution of this one is 1 at angle 90, 180, 270, 360. Will make one complete revolution of this one for making the conductor revolution to be represented in terms of the phasors using this particular notation. So minus j implies it is 270 degrees rotation without changing the magnitude. Okay, and like that. So in the parallel circuits, we know. Next, I would like to discuss the parallel circuits. The generalized the parallel circuit is RL, RC combinations. This is RL, this is XL, RC, and XC. And IL is inductive current, IC is the capacitive current, and I is the resultant current, total current, IL plus IC. And we introduce it because parallel complex impedances, Z is equal to Z1, Z2 by Z1 plus Z2, but we can use the admittance notation because the reciprocal of the resistance is conductance is well known, but we have not discussed those resistance, conductance circuits and others because you are familiar even in the undergraduate, pre-undergraduate level and intermediate onwards. So we go slightly in a different way in this, considering the admittance is reciprocal of the impedance by taking 1 by R plus JXL by notation. RL is the resistive component or the real resistance in the inductive branch, I would like to say. It is a simple notation. It is not that for the coil or additional resistance that can be connected in series in that particular branch doesn't matter. So RL plus JXL. So multiplied by the complex conjugate pair RL minus JXL in both numerator and denominator, you will get separated into real and reactive components, right? So it is still the reactive component, but this is called conductance. RL by RL square plus XL square, which is square of the magnitude of the impedance. RL square plus XL square under root is the impedance ZL. So R by ZL square is the conductance of the inductive branch, right? And this is the important notation is BL, that is susceptance. Susceptibility is the basic concept in this. How much is susceptible for the flow of the current, that is how much it admits, allows the current to flow through. Whereas in the case of the other things, we say that it opposes the flow of the current. Here it is opposite, parallel circuit. So it allows the flow of the current. So susceptibility, inductive susceptance is taken as negative, capacitive susceptance is taken as positive. You can see this notation, very important notation. So reactance, JXL positive, inductive reactance is taken as positive, and capacitive reactance is taken as susceptance. Inductive susceptance is taken as minus JBL. Capacitive susceptance is taken as minus JBC, and capacitive susceptance is capacitive reactance is taken as minus JXC, and capacitive susceptance is taken as plus JBC. Now you can see RL by RL square plus XL square minus JXL by RL square plus XL square is the admittance of the inductive branch. Similarly, for the capacitive branch, admittance of the capacitive branch is 1 by RC minus XC, 1 by ZC. Then RC multiplied by the complex conjugate pair of RC minus JXC, we get this separated into real and reactive component. That reactive component of the admittance is called susceptance. So capacitive susceptance is positive, whose value equal to BCY is equal to BC equal to XC by RC square plus XC square, and conductance of the capacitive branch is equal to RC by RC square plus XC square. And the total admittance of the branch will be YL plus YC, because admittance connected in parallel can be added, just as the capacitance connected in parallel can be added up, admittances connected in parallel can be added. So net admittance is equal to Y is equal to YL plus YC. Those things I have not mentioned here. It is only informally I have given these formulae. Now we will try to solve some of the questions that are being given in the competitive examinations. I hope you are able to follow. Now, this will take some time for understanding, because it can be sometimes 1 mark questions or 2 mark questions, and which is given in some of the gate questions. Not all of them maybe. Some of them which I have collected from the question bank, I will try to solve them. I have got the confidence that the answers that are given are correct. Otherwise, it is always I need to defend them. So therefore, it is debatable, right? So anyway, typically the current IT. Yeah, this is another one which I have to mention before going to that particular problem. Although it is, people might think that it is not related, but it is related in this particular itself. Because the example that I have taken, I have not given the formula correspondingly. I found later the problem is very interesting because this is from, people might think that it is a complex quantity which is being shown as I mentioned, as a Fourier series expansion I of t equal to I naught component, which is now called as DC component. Zero frequency components are also called as zero components. This I am talking about. Before going to the problem, I am explaining just brief theory about this. So plus sigma for n is equal to 1 to n Im into sin n omega t plus or minus theta, the phase difference. So n is equal to 1 is fundamental, omega t equal to some the angle. So n omega t. So similarly, n equal to 1 implies a fundamental component, n is equal to second harmonic and other things. So this is the RMS value of the fundamental component of the current. So the RMS value of the complex wave, which is represented as a Fourier series expansion or otherwise, is I is equal to IRMS. Assuming that Fourier series and other things are already known to you. Even this you might have studied, but I do not know whether you have studied in this particular angle or not. So the formula shows that it is I naught or A naught square, which is DC component square plus Im1 by root 2, that is I1 square plus I2 square plus In square. The derivation is good, derivation is there, but the point of interest is that it is an interesting property that, just as I have said, the phasor components of same frequency can be drawn in the same wave, same plane. So also here, because RMS value is integration of the quantity with respect to the square of the component waveform. So when you integrate that with the corresponding fundamental and other components, okay, when you integrate, first fundamental component interacting with second harmonic component, no current can flow through or the impedance will be infinite. That is, there is no cross fundamental frequency component that can be obtained for this particular one. That means the fundamental frequency component will not offer any impedance to the second harmonic component or vice versa. Second harmonic component of the current will not have any impedance that is being offered in the fundamental component of the current. There is a derivation for that, because integral of sin theta, sin 3 theta, sin some other quantities of the other angular frequency components called harmonic components will get nullified. They become nullified. In the sense they become zero, in the sense that they are mutually exclusive in that sense. The fundamental component of the current will not have interaction with the second harmonic, or second harmonic component will not have interaction with this. So cross RMS values will not offer the impedances. So also the currents offered are exclusive. So you can say I naught square plus I1 square plus I2 square and so on plus In square. So this being given in one of the competitive exams, I thought I have to give this particular one as the gate examination. So this can be pushed into the theory portion, this particular small item. Otherwise, now I will give the solution aspect of it. So in the given problem, now I repeat the statement of the problem. The current IT through a 10 ohm resistor in series with an inductance is given by I of t is equal to 3 plus 4 sin 100t plus 45 plus 4 sin 300t plus 60, right, degrees. A means amperes. The RMS value of current and power dissipated in the circuit are square root 41 amps, 410 watts respectively, square root 35 amps, 350, 5 amps, 250 respectively, 11 amps and 1210 watts respectively. So now the explanation to this is the fundamental component, that is I naught, DC frequency component. Zero frequency component is also called DC component. Okay. Later we are going to see also at a later stage in transients, in AC transients, how DC offset currents will be there. Even in machines you will study that, DC offset currents. So anyway, so those things from circuit point of view, now we are going to see that A naught is equal to 3, Im1, the peak value is 4, Im2 is equal to 4. So therefore, IRMS square is equal to I naught square is 3 square, and IM1 is 4 by root 2 square, plus IM2 is 4 by root 2 square. So 3 square plus 4 by root 2 square plus 4 by root 2 square is square root of that entire thing is 5 amps. So assuming it is pure inductive coil, no power will be displayed in the inductance, right? Therefore, power is displayed in the resistance only, right? So average power is IR square into R, IRMS square into R. So 5 square into 10 is 250. This is 5 square, sorry, it looks like 1, sorry for that. But anyway, so 25 and 10, 250 watts. So 5 amp and 250 watts. The answer is C. So it is, on the face of it, it may seem to be complex, but you have to understand there are so many small issues that are being there in this. This is the DC component, zero frequency component, this is the fundamental peak component of the voltage, this is the phase angle, this is the phase angle, and omega is equal to 300 here, and omega is equal to 100 here. So fundamental component is omega is equal to 100 here, third harmonic component is 300 here, all those things are there. But what we need is, these thing data is not all necessary. What we need to identify is A0, IM1, IM2 and IM3, etc. Then get the RMS value of the current. Once you know the RMS value, okay, and it is only 10 ohms resistance with an inductance is given by, in series with an inductance. So inductance is not stated as whether it's having internal resistance or the resistance and other things. So we can assume that it is, even otherwise the average power that is consumed in the inductive branch alone is 0. So therefore, assuming that is 10 ohms, we can get this one of the solutions. If you find, if the resistance of the inductance is also given and you find another answer, it is debatable. So I assumed that based on the assumption that I made, that average power that is consumed in inductance 0 and 10 ohms resistance, we have got the power that is being obtained as I square into R. So therefore, we have got the RMS value, the complex wave is obtained in this particular way, is I naught square plus I1 square plus I2 square, etc. So here the DC component is being given, third harmonic, first harmonic, fundamental, third harmonic components are being given. So the RMS value of the complex wave is I naught square or A naught square plus I1 square plus I2 square plus I3 square and so on. So that is RMS values. RMS value is IM1 by root 2. IM1 is the peak value. IM2 is the peak value of that. So based on that, we have got these values being substituted, and the average power is only in the resistance that is being considered. So average power equal to I square into R. So is equal to 5 square into 10 is 250 watts. So I hope you are able to follow. Anything, if you make another assumption, you may get another one. So the assumption must be right. That's what I feel, right? So next one, there are umpteen number of problems are there in solving these AC fundamentals. A few only I have selected for illustration because we have got limited time. One unit is to be covered in a span of 1 hour of lecture and 1 hour of object type questions and other things. Keep on doing it. So it is only one part of the subject in the GATE syllabus. So we try to cover in these things. And definitely, if time permits, and if you are interested, we can have interaction at a later stage also, either through Google Meet if the university permits us to have another session at a later stage, or if you want to have interaction, I will give a corresponding email ID and contact numbers. And because people are afraid of misusing, I hope our students' electricals are straightforward, they will not misuse. And I will say always that you should not use shortcuts. Shortcuts always will be dangerous, which may go to the short circuits. So I will be highly interactive at a later stage, and after these fixed slots are being provided, so I can interact with email ID if you want that to be given at a later stage. So for the subsequent this one, we can have interaction through either through personal Google Meet or through email correspondence, or even through phone call. I can give that particular one with specified timings. So I like that concept, which is given by IIT Chennai some 3 years back under QEEE. Talk to your teacher. Of course, I am a retired teacher now, but still I can use that. Having got a lot of service that I have done in university, I can extend that. Now I am more free to spare more time to you if you use it properly. So I mean, whatever little I know, I can give my thought-provoking ideas to you. And in the process, I can also gain some knowledge irrespective of the age, so that we can have the fruitful discussions in GATE, and that will be useful not only for GATE, for the other engineering service examinations or UPSC or UPSC or any other competitive, even railways examinations, etc. So many competitive examinations, the fundamentals are going to be same. The testing levels are going to be different. Right. So now let us come back to this particular one. Just to have some small break in that, I have given some few tips for understanding. I got some few questions on this for solving. I will explain in the next time, remaining half an hour or 40 minutes, because we lost some time. Because I hope it's not monotonous. Even I am not also going very fast, because we need to understand these things. And so in the meantime, maybe you might have written the question also, but anyway, I will read out, I will repeat it, and then try to give the solution to this. In figure, A1, A2, A3 are ideal ammeters. If A2 and A3 are read, not read, because read, present tense, past participle are same for that typically in English. Read 3 amps and 4 amps respectively, then A1 should read. Now this is read, should read. What is the value of A1 that is being asked? Here the inductance is there, current is flowing is 3 amps given. Here the resistance value is not given, R is given, 4 amps is given, the AC source. So under steady state, it is all implied that it is under steady state. The multiple choice questions are being given. Those days none of these are being given. Some people now in our university or other competitive examination, we don't want to give this none of the above, because people are so clever. They answer none of the above and say the way you have given that choice and other things unnecessarily. People have been cornering. So you have to give some valid or invalid answers for verifying these things. So the options that are being given are maybe this is given way back in 24 years back, right? 1996 gate question paper, this has been given for 1 mark question. So so 1 ampere, 5 amps, 7 amps, none of these, right? So 3 and 4 are the parallel currents, and we want to get, and if you want to take the arithmetic sum, it is 7 amps, seem to be right. And if you take the difference of the current, because we do not know how our mind works at that time, 4 minus 3 is 1, 1 ampere is also there, none of the above, maybe all the answers are not being correctly given. There is another one, 5 amps. How this 5 amps, 3 plus 4 is not 5. How this is being obtained? Because this is, maybe that is another option, or none of the above. Now these two are being eliminated because it is not the arithmetic. 7 is arithmetic sum, which is not correct. And the difference of the currents, because it is only same source, and the current division rule says I is equal to I1 plus I2. It is a phasor sum, not the arithmetic sum. That is clear now, because this is a AC circuit and the components are R and L. It is not both are same resistive elements. So if it is both are resistive elements and same source, then it is definitely the algebraic sum is same as the arithmetic sum. But this is now the phasor sum. Now you have to differentiate between the arithmetic sum, algebraic sum, phasor sum of the quantities, because it is AC circuit.
Resign I have to do, sir. Okay. సార్ ఎక్కడి నుంచి మొదలు పెట్టాలి?
అంటే ఇప్పుడు 7th grade లో అక్కడి నుంచేనా లేకపోతే sorry for the interruptions and there is no trouble. Anyway, we could get the access back again. So it's not the time, it is the total, the way which we have to answer is very important. So now, yeah, so I read for sake of continuity once again. In figures A1, A2, A3 and are ideal diameters. If A1 and A3 are real, read 3 amps and 4 amps respectively, then A1 should read what is the value of this one. So there are two values of the ohmic values are being given, R and L here. So these are of different nature. So we have to use a complex addition here, phasor addition. So I3, right? I3 is 4 amps, which is resistive, and this 3 ohms is I2 is 3 amps, which is reactive. So inductive, right? So this is 4 plus J3. So therefore I1 is RMS value of the current of this one is magnitude of 4 square plus 3 square is 5 amperes is the right answer. So it is not the simple arithmetic sum, it is not the difference, and it is only the phasor sum. None of the above is also not right answer. So it is only phasor sum of the two quantities that gives the total current here. That's what we have to understand from this particular one. I hope you are able to follow this. So now I have got some more problems. About 3-4 problems are there which I would like to discuss. Maybe we are losing time. We have lost about 15 minutes time, so that will be compensated. It may take up to 5:15. So please bear with us, and because there is no interaction directly, I am unable to know whether you are able to follow it or not. But anyway, our admin system are understanding or checking that if there is a problem with the transmission, they are asking us to rejoin it. So that is why there is a small break in that because of some discontinuity in the power supply, perhaps, although we have got inverter connection, because of that maybe we have to rejoin, and because of the power supply failure in the house, that can happen. Okay, so these are practical problems. We are the power engineers, so we have to solve these problems. So lucky that today we are able to have provision of these things sitting. Thanks to Corona, we are forced to use the recent technologies, that is online coaching or online teaching, etc. And I am happy to do that because I am a retired person, having got the opportunity to sit in my house and then do it. It is a typical experience for me. Although I have given webinars earlier, but sitting in the house and giving presentation like this through Google Meet is a first time experience. Although we arrange in IEEE activities, I was the past chairman of the IEEE in that context. So anyway, now let us come back to even I attend the webinars which are being conducted. For students also we are conducting webinars. We will be sending emails to you at a later stage. Now we will be connected to us later. After these 10 days lectures, if any webinars are being arranged under IEEE, we will definitely inform you. Just similar to this, you can log into that with the limited participation of 400. But now we have got even thousands of students are appearing for this through Google Meet. Okay. So even IEEE we provide through Cisco WebEx meetings. We have been arranging, we are giving lectures, we are attending to the lectures of the IEEE from Hyderabad section. We have got subsection here. Anyway, so this just to have continuity of this one. Now I will go to the next problem, which is which I have taken. So a 230 volts RMS source supplies power to two loads connected in parallel. That is a parallel circuit problem. The first load draws 10 kilowatts at 0.8 leading power factor, and the second one draws 10 kilovolt amperes at 0.8 lagging power factor. The complex power delivered by the source is, there are 4 multiple choice answers are being given. Complex power means in volt ampere rating or kilovolt amperes that is being given. 18 plus J 1.5, 18 minus J 1.5, 20 plus J 1.5, 20 minus J 1.5. So that is a given problem. I repeat the statement of the problem. You can note down, but anyway try to understand in between, because while I read the question, you should try to solve it in the way in your mind which you can do it perhaps. A 230 volts RMS source supplies power to two loads connected in parallel. The first load draws 10 kilowatts at 0.8 leading power factor, and second one draws 10 kilowatt amperes at 0.8 lagging power factor. The complex power delivered by the source is, the multiple choice answers are being given. So the circuit diagram that is being drawn for this particular one is V is given as 230 volts, that is shown as 238 angle 0 is the reference phasor, and it is leading power factor. For the first one draws 10 kilowatt at 0.8, so it must be RC circuit because it is predominantly capacitive. Leading power factor that means RC, no other choice. So we have to treat it equally as RC series circuit, predominantly capacitive. And second one is 0.8 lagging power factor circuit with 10 kVA. Complex power is being given here. That is the only thing. So S is given instead of the real power. Here real power and power factor is being given. Here complex power and power factor are being given. That is the notation to be followed. Okay. So I is the total current. The complex power delivered to the source to be obtained. So V into I conjugate must be obtained. So that is why I have drawn this circuit. Total current I have not written here. Sorry. So I1 is the capacitor, the predominantly capacitive one, and I2 is predominantly inductive, right? So the power drawn in this is real power 10 kilowatts, that is P, and this is power factor is cos phi L, and this is capacitive branch. Complex power S is given as 10 kVA, and power factor lag, this is 0.8 power factor lag. Now in the first branch, real power, it is not real, sorry, it is real, REAL. So real power P is this one power is equal to 10 kilowatts. So V into I1 or inductive branch current by cos phi, P1 by, because P1 equal to VI1 cos phi, I1 is equal to P1 by V cos phi. So 10 kV, 10 kilowatts. So 10 into 1000 or 10 cube divided by 230 into power factor is 0.8 gives you 54.34. So 50, this is 54.34 amperes. Expressed in polar form, you know, Cartesian form and polar form of A plus IB or R at an angle theta and other things. Because with respect to the voltage that is chosen as this one, the current being leads, the angle is can be easily obtained as 36.86. I hope you know these calculations, and that in internal details are not being given. So in the second branch, S is equal to V into I2, because I2 is equal to S2 by V, because S is the complex power that is being given, S2 by V2. So 10 cube divided by 230. Earlier that is real power that is being given, but it is complex power. So V is 230 at an angle. So 43.47, and the angle is 43.47 at an angle of minus 36.86. Okay. So cos phi and sin phi can be obtained for these things, which I have not shown here, that I hope you are more familiar. Okay. So yeah, this is given in GATE 2014. Okay. So in phasor form, I2 is equal to 43.47 at an angle minus 36.86. Okay. And I is equal to I1 plus I2. Right. So it is a phasor addition. So this phasor addition, it is not directly 54.34. So you know that R1 at an angle theta 1 plus R2 at an angle theta 2 is not same as R1 plus R2 at an angle theta 1 plus theta 2. So people should not get confused. By now you are more familiar with this type of complex calculations. This polar form is to be converted into R cos theta plus J sin theta, and this is to be converted into R cos theta plus R sin theta, J R sin theta plus or minus, and therefore this addition is to be done complex way, right, in complex variable form. A plus IB plus or minus, A plus or minus IB, and like that. So this is not the arithmetic sum, it is not the algebraic sum, it is a phasor sum. There is a difference. So this phasor sum again in polar form, expressed in polar form is sometimes easier, but again you need to convert that, okay, because the answer is given in complex form, that is a Cartesian form. We need to convert this into the Cartesian form. So R at an angle theta plus R1 at an angle theta 1 plus R2 at an angle theta 2, and because it is a leading power factor angle with voltage, current leads, here and the current lags the applied voltage. So therefore plus 36 angle here, 36.86 is second one. So this is not simply the arithmetic sum of the two magnitudes here, no. So that is R1 plus R2 at an angle theta 1 plus theta 2 is wrong. So it is complex addition. So real terms should be combined together. Imaginary terms should be combined together. So therefore we can get these things carefully. So you can see how much work is involved in solving these problems. Luckily this particular problem is being solved in the book. I don't mind giving the reference because it is only complete. It is not copying. We have to try to only verify these things. Earlier yesterday I mentioned made easy publications GATE 2019 electronics engineering. And they have given they have given solving problems also. The others are yesterday I told you the 32 problems or 32 year problems have been solved. Yeah, the others names are given in the inside. No, chairman's name is given. Anyway, it is surprisingly the others names have not been given. So maybe it's a collection of so many other solutions that have been given. So GATE 2009 electronics engineering question bank previous solved papers by made easy publication, ME publication, made easy publications, right? So they have given 32 years of solved problems. Also it is for electronics engineering. If you have got it, you can get it. Okay. Anyway, so this is one of the so current is being obtained. So complex power delivered by the source P equal to VI conjugate. You know, conjugate is to be written. If V is taken as the reference, V into I conjugate, and I is taken as the reference, I into V conjugate. These things are quite common. I have not mentioned that. You must have been familiar with this. Otherwise, I can repeat it if you want at a later stage. So that is why I have kept 1 day buffer. If you want to explain me, all the material is available with me, either through PowerPoint presentation or even orally also I can explain. The material is hard copy, written copy is with me only. So therefore, I can have question and answer being explained also at a later stage also given the opportunity. If you are not able to understand on the face of it in today. I hope you are able to follow. Assuming that you are able to follow, I can go to the next one because we have got some more problems to solve. And once I complete, then we'll say some more instructions and wind up subsequently. I got 2 hours time, 3 to 5, because there were some interruptions for about 15 minutes today. I may extend up to 5:15 maximum. Yeah. Now I have taken another example. There are 6 examples total I have taken. So 3 more problems are there. Some of them are complex, some of them are easy and other things. Now you can see it is not a multiple choice question. And the 4th question which I have collected is the voltage. VC across the capacitor in volts in the network shown is dash. So it is what do you call answer to the dash. It's not multiple choice question. One word answer like or the value like voltage across the capacitor only is to be obtained, is to be given, right? So this is an RLC series circuit problem, and the value is the supply voltage source is alternating voltage, 100 volts, and F is the frequency. This is the standard representation of the AC source, and the circuit is having R is equal to 80 volts. That is voltage across resistance is given, not the resistance value. So that is the circuit is given as it is, has been written like that. Then we'll try to understand what that is being given with our notation here. So 40 volts is the voltage across the inductance that is being given. VC is the voltage across the capacitance that is being given. And remember that these are all ideal elements that have been considered. If you consider the internal resistance of this, again this has to be shown as series inductance only, that is RL series combination. Practical inductance implies RL series combination always. But anyway, these are simple RLC elements are being shown. Each one of them are ideal values. Okay, capacitor is ideal value is inherent parallel resistance. That is a typical concept. Most of the times the shunt capacitance of the internal resistance of the capacitor is negligibly small as compared to the inductive circuit where the internal resistance is taken as series. This nobody explains most of the times, but this point is to be understood carefully, because when I talk about internal resistance, when both components are there, what about the internal resistance of the capacitor? Internal resistance of the capacitor can be treated as the shunt capacitance, but that can be treated as very, very negligibly small. That means it offers almost infinite resistance to the circuit behavior because capacitance is predominant in that. Ohmic value of capacitance is more dominant than the resistance value of the capacitance. That is why its value is negligibly small. But it is ideal capacitor here. But in the case you want to include the internal resistance of the capacitor, it can be taken as infinity. But whereas the internal resistance of the inductance, if it is not negligibly small, you have to show that as the resistance. So that instead of simple inductive branch here, you have to show that as RL series combination. But anyway, since nothing is being mentioned, there is nothing wrong in choosing them as the ideal elements. That is important, right? So the voltage across resistance is given as 80 volts. The values of the RLC are not being given. The value to be computed is the voltage across the capacitance, right? So we know the phasor addition of the voltage or the corresponding complex value of the voltage is V. Supply voltage is equal to VR plus JVL minus JVC. It is a complex value. Given VR is equal to V is equal to 100 and VR is equal to 80 plus J, VL is 40 volts minus VC in complex form. So now we know in the complex form when you have got some V is equal to VR plus J VL minus VC, now the magnitude can be computed as V square is equal to square root of VR square plus J VL minus VC square, right? So therefore that is what I have written here. So it is a magnitude of the corresponding complex form of the voltage. Total voltage V is 100. This is VR 80. This is J. VL is 40. VC is to be computed. So V square is equal to VR square plus VL minus VC whole square. So V square is equal to 100 square is equal to 80 square plus 40 minus VC whole square. So VL minus VC whole square. This point is based on the RLC series combination of the circuit configuration, which we can write down easily. This is the complex voltage. V is equal to VR plus J VL minus VC. Okay, that is that is to be struck into our mind. That is the only way, right? So 40 minus VC whole square is equal to 100 square minus 80 square. So this is A square minus B square. So 100 plus 80 into 100 minus 80, which gives you 180 into 20 is 3600. So 40 minus VC is square root of that. So because 40 minus VC whole square is 3600. So therefore taking square root of that implies, okay, then taking the square root gives you 60 here and 40 minus VC. So since 40 minus VC equals 60, so therefore VC is equal to 100. VC is giving minus 20 plus or minus. Okay, yeah, okay, yeah, plus or minus you can take. So therefore its value is 100 volts. So that is clear. Yeah, that is 100. So that means you can take it as a minus value also sometimes because it is capacitive voltage. 40 minus VC is minus 60. So VC is 100 volts is answer that is being given. So maybe if I got carried, I need to justify it. Okay. Otherwise, this is giving minus 20. Okay. So 40 minus VC, I can make it conveniently 40 minus VC or VC minus 40. Because it is squared. So internally I can make this as VC minus 40 whole square is equal to 3600. That way I can show this. So VC minus 40 is equal to 60 implies VC equal to 100 volts. So there is you can see anybody can fumble at any time. You can get carried away. This can happen to anyone, right? So one has to be careful about this. I hope 100 volts is the answer that is being given as the multiple answer, which is correct. So 40 minus VC, you could have written this as for VC minus 40, then this problem would have been solved. Otherwise, it gives the wrong interpretation because instantaneously I have stated that minus 60 I have to take. That is not appropriate. So because VC minus 40 is 60, sorry for the inconvenience. So because sometimes our thinking will be just going away because of these reasons, because we know the answer. That can happen. Okay, sorry for these things, but anyway, sometimes it is a fetching point. If we do tell things wrongly, we can correct them, and why it should be wrong also, we have to justify it. So that is where in the analysis part, not that we are teaching the wrong things, but because it is a competitive examination preparation, how best we can go for the wrong things also, simply we can get carried away also, will be able to be known here. I don't feel shy for making a mistake in this, because human can be erroneous. But are we consistently doing the same mistake, or can we justify that this one, or make amendment to that particular one? His judging capacity also must be made. And now you can see this is not given in the GATE examination, but in one of the competitive examinations. So, so I hope you are able to follow this particular one. So it is VC minus 40 is equal to 60, because I cannot make 18 here. So please bear with me for the small mistakes, so which can be rectified. So VC is equal to 100 volts. So if there is a mistake, then I have to rectify it, because if 40 minus VC is 60 implies VC is equal to minus 20, doesn't make any sense there. So anyway, I hope this must be taken as VC minus 40 for solving this particular problem. So if there is any doubt, you can send it through Google form. We will rectify that particular problem. So I hope you will be interactive in this sense. You understand the difficulties in this, and then try to have more interaction, because it is only interactive section that will make us more useful for between the teacher and the student in this particular context. Okay, it is not the testing capacity of the individual teacher to the student for these things, but ultimately the student get benefit of the correct solutions, the correct way of approach of solving the problems and other things. Okay. I got two more problems, fifth and sixth. I got 6 problems. So for illustration, only samples. It's not that is the total end of these things. So one again, I mentioned that it will not be repetitive always, but attempting the problem in right direction is quite admissible thing to be made. సో కరెక్ట్ పంథాలో వెళ్తున్నామా లేదా సొల్యూషన్ అనేది మనం ఆలోచించుకోవాల్సినటువంటి పరిస్థితి అయితే వస్తుంది. దీనికి సొల్యూషన్ మనకి కనబడుతున్నట్టు ఉంటుంది, అది కరెక్ట్ అనిపించేస్తుంది తక్కువని. సో యూ హ్యావ్ టు థింక్ ట్వైస్ బిఫోర్ పుట్టింగ్ ది రైట్ ఆన్సర్ దేర్. ఇట్ మే బి రైట్ ఆర్ రాంగ్, విల్ బి జడ్జ్డ్ బై ది ఎగ్జామినర్, ది పేపర్ సెటర్ ఆర్ evaluator subsequently. Even now it is online examination, online evaluation, everything. So therefore all these things have to be fed correctly. If the right answer may be fed wrongly, or wrong answer is fed wrongly, and matching wrong goes, we cannot, such mistakes will never happen. A lot of care precautions will be taken by the system. The feeding people, verifying, all these things will be done, because we have got some of these experiences while setting evaluation and other things. One has to be careful about these things. Anyway, so it's not the experience alone, it is a meticulous way of doing things is that matters. So anyway, next question is, these are some of the tips. It is not monotonous teaching. The tips in understanding, the tips in evaluating, the tips in approach in solving the problems in GATE preparations or any competitive examinations, you should be able to follow these things, keeping these things in mind. Okay. So it is only a practice session. It's not that the same problem I am going to give you, or you are trying to solve, I am committing mistake and other things, and then telling the wrong answers or otherwise. So it is interactive sessions we would like to prefer in the GATE online coaching classes subsequently. Okay. So anyway, RMS value of half wave required symmetrical square wave current of 2 amps is root 2 amps, 1 ampere, 1 by root 2 amps, root 3 amps. I repeat the statement of the problem. You can take 15 seconds for understanding the question, and by memory or virtue of your knowledge, you should be able to get the answer by now. So that is how the small simple problems are like this. Okay. So the RMS value of a square half wave required symmetrical square wave current of 2 amperes is root 2 amps, 1 ampere, 1 by root 2 amps, and root 3 amperes. So earlier I have mentioned that in the principles, the first few slides in the steady state analysis, the RMS value of a square wave is unity. So with a magnitude of root 2, okay, with a magnitude of root 2, 2 amperes, RMS value of the half wave required is 2 amperes. So I square is equal to 2 amps. So therefore the RMS value is now root 2. So if you understand this particular one, if it strikes in your mind, the answer is simple, within seconds you will get. So we have to remember this particular tip, that the RMS value of a symmetrical square wave current of 1 ampere is 1 unity. The magnitude is twice here, 2 amperes is being given. So therefore I square is equal to I, instead of 1 you have got 2. So I square is equal to 2 means it is root 2. So answer is A is the multiple choice answer. This is being given in GATE 2005 for 1 mark question. So it is just 1 mark question. Yeah. So this is the last but not the least question, which is there are umpteen number of varieties of problems are there. I have collected only a sample of 1 hour theory or together with the explanation to the solving the problems for 2 hours. I have taken appropriate time for choosing this. So this particular problem now, and before finding up some the solution to this particular problem and giving 2 minutes for what I am going to take up the next and what the corresponding instructions to be given to you, we will mention that before we wind up. And so for a triangular waveform in the figure, yeah, sorry, this gives the wrong impression because while cutting off there is a small error here. This GATE 2005 is for the previous problem. Okay, so now this is yeah, this is also given in GATE 2005 luckily, but that is written at the bottom. Okay, this GATE 2005 is for the previous question, which I have written at the bottom that this question is being, that question was given in GATE 2005. Okay, and now you can see for the triangular waveform in the figure, the RMS value of the voltage is equal to, so object type question, multiple choice question, square root of 1 by 6, square root of 1 by 3, 1 by 3, D is square root of 2 by 3. So I repeat, for the triangular waveform in the figure, the RMS value of the voltage is equal to, now you can see the x-axis is time t, and from 0 to t by 2 is ramp, this ramp function, and t by 2 to t, its value is 0. Similarly, second cycle, t to 3t by 2 is again, so it is a periodic waveform, right? It's not non-periodic waveform, it is a periodic waveform. Non-periodic waveforms are known as aperiodic waveforms. Aperiodic is non-periodic. Yeah, periodic means it is a periodic waveform. Recursively, for every cycle of time, it is repetitively is periodic waveform. It is a periodic waveform. It is different from, it is a periodic waveform. Aperiodic. Aperiodic means gives a negative meaning there. Non-periodic waveforms are called as aperiodic. Okay, only just A is added or A is separately shown. That makes the difference. So you have to understand English also in this case. So one has to be careful in telling these things also. So we cannot be casual in this, but we need to understand. So it is a periodic triangular waveform, right? So 0 to t by 2 it is ramp, t by 2 to t its value is 0. Similarly, second cycle is t to 3t by 2 is same ramp with unit magnitude, right? So it is ramp or triangular wave shape. This is called ramp slope, right? That is called ramp function, right? So it is also referred as triangular wave shape, right? If this is not there, it is called ramp. It is a linear straight line passing through origin. So there is ramp function up to this. Anyway, so for the waveform, sometimes the solutions are not being given. You have to do these things, which is given in GATE 2005 problem. It is given in other question bank, but this is not a solvable problem. Okay, because some of the problems can be easily done. I have done it on my own, but some luckily for some problems there are solutions given. The solutions, as I mentioned yesterday, however complex may be, I have to find some time to do these things, and then it is not copying, it is only verifying the answers and then trying to explain to you. That is why I have taken those examples. So similarly, we are going to have a good number of examples, so they are given in GATE examination in tomorrow's session also. That is resonance I am going to discuss. Now for the triangular waveform in the figure, the RMS value of the voltage is equal to be computed. 4 multiple choice questions are being given, answers are being given, square root 1 by 6, square root 1 by 3, and 1 by 3, square root 2 by 3. For the waveform shown, the equation can be written as, now this is the slope. The slope is this magnitude, that is vertical component divided by y by x, you know that, okay? So because it is passing through the origin, it is y by x into t. T is the corresponding x-axis. So v of t is equal to y by x is 1 divided by t by 2 into t. So 2t by t, in other words. For 0 less than t less than or equal to t by 2. So writing the waveform equation is also equally important. And its value equal to 0 for t by 2 to t. So that is being written as t by 2 less than t less than or equal to t. These are the equation is being written in normal fashion for this particular wave equation. This is called equation for the waveform is also called as wave equation, but wave equation is something else when you study in power system solutions. Okay. Anyway, so RMS value is v square t is equal to 1 by t integral 0 to t v square t dt. So since t by 2 to t its value is 0, so it is only from 0 to t by 2, and v square t is 1 by t by 2 whole square to t square. So this is finally the solution that is being obtained. So 1 by t is here, and this 1 by t by 2 whole square is 4 by t square into 4 by t square, taking the integration of t square is t cube by 3. So it becomes 4 by t cube here, substituting t by 2. Some of the terms getting cancelled, its value becomes equal to 1 by 6. So VRM is equal to square root of 1 by 6. So the answer is A. I hope you are able to follow it. So this is all about now just giving the gist of what I have explained today. Okay, in the next 5 minutes I am going to wind up, and these are the examples which I have collected, and that is the end of the explanation to the problems. If you have got any questions, you can post it. In the meantime, I will just briefly mention in 1 or 2 minutes what we have studied today, or what I have just discussed today, including the solved problems for gate preparation and other things. Because the entire text cannot be given for a particular subject, because it is a 2-semester subject covering in 2 hours in different slots. I have made that into 11 slots, because some of you might have joined newly. Then this is the second lesson. Yesterday we were discussed with the DC circuits, KCL, KVL and source transformation to some extent. Today I have discussed magnetic circuits and a basic series parallel connectance of the capacitive circuits. In magnetic circuits I have discussed with mutual inductance properties also. So series rating, series opposition, and in parallel case also I have just given the formula and solved some simple problems in which are sometimes given in gate or non-gate examinations, other competitive examinations. I have collected some sample examples for ease of illustration, for ease of understanding and delivering the things. And later, after that, I have done steady state analysis. The steady state analysis implies for AC circuits. For AC means sinusoidal wave, defining initial value, the instantaneous value, the peak value, RMS value, form factor, average value, and current flowing through the resistive circuit, inductive circuit, voltage being applied, capacitive circuit, and phasor relationship between voltage and current, difference between scalar, vector and phasor, which is very, very important. The difference between the arithmetic sum, algebraic sum, as we have done yesterday, and today one more addition is phasor sum addition, complex quantities additions. All these things are very fundamental, but I have done the explanation of all these things, and then simple RLC circuits, then RL combination, RLC series circuit configurations, and just one example of the parallel combinations, and with RL and RC parallel combinations, and a concept of the impedance being mentioned, and that some more examples are going to be there in tomorrow's lecture also, which I will mention it. And so I have done that. Good number of examples have been considered. Three examples for magnetic circuits, 1 or 2 examples for capacitive circuits, and 6 examples in the AC circuit analysis now, including series parallel combinations, etc., and even the triangular wave shapes for finding the RMS value, etc. So about 10 examples I have done. Some of them are given in gate, 1 for 1 mark, 2 marks. Some of them are given in other competitive examinations. Okay, and a lot of work has to be done before doing this particular one, because I need to. Some of the solutions are not being there. Only answers might be given. In some cases, solutions are being given. Some books I have mentioned already. So I hope you have noted down. If you want me to do that, I can do a separate slide at the end. For those who want to know about those things which you could not get, I can give the details of the books, publishers, and other thing. Nothing confidential about that. It is already some teacher has or some professor has might have done that job already as a collection of the resource material. So therefore, there is nothing wrong in getting understanding through other things, because for competitive examination, the style of preparation could be different. So therefore, I have done some 10 examples of competitive nature, tried to explain even one may be slightly erroneous. Let us see. I think that is correct, but we need to verify that particular one. So if anything wrong, you can point out. We'll do it again at a later stage. So tomorrow I'm going to discuss resonance, series resonance and parallel resonance circuits, and some interesting problems to be solved in the GATE examination question papers. Some of them are solved by the books written by some of the authors in some publications like ME publications. Some of them are not, but answers are being given. Why I have chosen such problems is we can have the confidence that whatever we are doing is right, and that is being verified with the solution already given. Sometimes it may be a problem that normally nobody gives wrong answers in the multiple choice object type questions in the printed manner. But if some people are given wrongly, we may get carried out. So, because we may be tempted to based on the solution that is known. Normally, we will solve it and then verify it. Sometimes you may be tempted if its type is not sufficient or you don't, you are overconfident. You may be tempted to say already, it's very clear. I know the answer. Suddenly, we jump into the conclusion that this is the right answer. But while doing meticulously, we may get another solution. So that is where some of the things which I found wrongly are got wasted because I found them wrongly. They are being quoted, and unless I am doubly confident about it, I should not present them and confuse to you. So therefore, I have not selected those things. I have given only those problems which I am confident. Solutions are being given, answers are being given in some cases, solutions are being given in some cases. So like that, I made a small attempt in making this. Lot of effort has been put for making these presentations, and I thank the authorities. Before winding up, there are instructions also. I will mention it. So tomorrow, please be present at 2:55. With all your preparation and logging details that admin already has provided to you. And same yesterday's one or two questions I could not understand properly because complete sentence are not being given to us. So maybe tomorrow, today evening, today's doubts and or any clarifications or other things can be given by today evening. So tomorrow I will try to address them. That is one thing. So you try to fill the things in Google form, and the interaction can be through answers that I will present it in the next session tomorrow at the same time. So I will be discussing about resonance, series resonance and parallel resonance. They are also referred to as tuned circuits. Even electronic students can attend to these particular course in electrical circuits. So particularly I am referring the electronic engineering GATE syllabus solved problems textbook also published by ME. So subject is same, right? So whoever gives the appropriate material, there's nothing wrong in collecting such material. We are not confined to only electrical engineering. We are electrical and electronics engineering because electronics engineering is originated from electrical engineering. Okay, so we study about those things, resonance and resonance, essentially series resonance, parallel resonance, configurations, etc. Solving a good number of examples like this. About 6 to 9 problems I have collected. I will tell you those things, and you try to, if possible, you view the Google form these things by now. Probably tonight I will get it. By tomorrow afternoon, if I get them, I will get those things. I thank you all for giving me an opportunity to rectify the small problems which we got yesterday. Even you commented that yes, it's not a comment, it's a good sign. So to use the even mouse, so I could get the mouse today. So therefore I could present to my satisfaction as compared to yesterday. And we have made the PPTs also as compared to yesterday. One full sheet is one PPT slide. Instead of that, we have split that into two. But the original PPTs could not be made in the sense handwritten only I could make because circuit diagrams, drawing waveforms in this one still we have to make an attempt. Maybe we'll try to do it in subsequent this one, but not in this first phase of lecturing in the next 10 days to go. We've got 10 more sessions to follow. So such of those who are logged in late also doesn't matter. Tomorrow also you can join. Each one can be, because this is only memorizing and understanding the not new concepts, the how to solve the problems only. So therefore you can always attend to these lectures because you have studied all these things in your first year or 2 semester course in 1-1, 1-2 or 2-1, 2-2 or 1-2 and 2-1 respectively, whenever it is being offered over the decades, right? So therefore, anybody, even EEE EC students also can attend to this particular one, or allied branches. Those who have studied circuit theory and have got gate questions, circuits is as one of the subjects is being there, they can attend. Need not be from EEE alone. I hope there are other students, other engineering branch students also there. It is interdisciplinary nature, this particular subject. A very fundamental, hardcore, heart of the electrical subjects I would like to quote, and electrical circuits and network theorems will be heart of the electrical subjects which we'll be studying subsequently. So I thank for registering for this particular one, and I thank the university authorities, Honorable Vice Chancellor and Director of Urban Planning for arranging all these things, and Mr. Bharat, Mr. Surendra for giving all assistance to me in making these PowerPoint presentations, and all those staff who are directly or indirectly connected in supporting, particularly Mr. Venu, who has been a computer programmer, who has been helping me in making this, how to go about making these PPTs to be presented also. He has helped in first day. So there, like that, is a collection of team effort. Only subject content I have prepared, remaining all, it is a team effort. So I thank all the team members, and I am gratefully acknowledge thankfulness to our Honorable Vice Chancellor who has given me the opportunity to present before you the subject electrical circuits, which is a fundamental hardcore subject and very fundamental subject. So thank you very much. So we will wind up the session. Thank you. So tomorrow we will meet at 2:55 p.m. Thank you.